Welcome to another session on thermodynamics. In this session, we are going to talk about the first law of thermodynamics. In the last session, we introduced different terms involved in discussion of thermodynamics, like what is a state, what are different types of variables that is required for defining a state of a system, what is a system, what are different types of processes, thermodynamic equilibrium, what are different types of equilibrium, and so forth. So in this session, we are going to talk about first law of thermodynamics. So to give an historical perspective of the development of the field of thermodynamics, we can start by talking about the Benjamin Thompson, let's say 200 years old story, where he first linked the work with the heat when he was working for building cannon. So what he observed is that when you rub the cannon surface, then you are basically doing some work. And in that work, friction is involved. So that results into the heat. So that's the first instance when somebody related work with the heat. Then Nicholas Carnot, he talked about the different types of processes. And he is the person who developed the concept of engine, right? At that time, people were talking about this something called perpetual motion machine, where they were talking about developing one machine which could generate energy forever and which can convert energy into work, and that also with efficiency is equal to 1. That means without losing any energy. Then comes the case of Joule, who was a brewmaster, means he was working for making beer. And what he found out is that when he stirs the beer, the fluid, then the temperature of the beer gets increased. So again, stirring means working. So you work, raise the temperature. So that means you are converting the work into another form of energy, which is heat. So thermodynamics is the subject that deals with the heat energy conversion from one form to the another. So there is a funny story during those days, early days of the development of thermodynamics. What people were thinking that the heat is a form of energy which flows like liquid. So it always flows from a system which is at a high temperature to a lower temperature. So it's like water flowing from a higher place to a lower place. So at that time, they thought that heat must be something like some particle which is taking away heat from one place to the another place. And at that time, they were also thinking that those particles are not visible yet, but someday they will be able to find those particles which are responsible for the flow of heat from a higher temperature to a lower temperature system. Okay, so of course, there is nothing like that. The heat flows because of transfer of energy, but that transfer of energy happens in a microscopic manner, in a different way. So in this part, you have to remember that whenever there is a flow of energy, then we have to identify those change in energy with some signs to understand whether the flow is into the system or out of the system. So if the energy is added to the system, that change in energy is positive for the system. And when the system is such that energy is taken out of the system, then that is a negative. That change is associated with the negative sign for the system itself. Then next, let's talk about the work. Work is another form of energy, but of course it is different from heat. And work, a system can do some work, and that's how the work is flowing out of the system, and some work may be done on the system. So that means the work is going into the system. So that's like a flow of energy from the system or out of the system. But one thing that you have to understand, that work and heat are different form of energy. Like if you have a book and you raised it from a lower height to a higher height, then you did some work. And due to that work, there is no heat change in the book, but there is a change in its internal potential energy. And that's a gravitational potential energy that just changed. So you did some work, but no heat got changed. So that's how you can say that they are different. Sometimes it does, sometimes it doesn't. So you can convert from one type of work to heat, not all. Then there is something called internal energy. The internal energy of a system is the energy that is sum of all types of energy that the system contains. It could be kinetic energy or different form of potential energy. And those potential energy could be configurational potential energy, bond energy, other form of interactions like electric interactions. Let's say there is a gas in plasma phase, so ionized gas, and you placed it in with an external electric field, then there would be for all these ions, they would have some electrical potential energy. So that also contribute to the internal energy of the system. So internal energy basically encompasses every form of energy that the system has. So those, let's say a system of gas molecules, those gas molecules are moving, so they have some kinetic energy. So that's also part of this internal energy, right? So again, just to remember, you are giving some heat energy into the system, or you are working on the system, then that change in this energy of the system is positive. And if any energy is taken out of the system, the change in energy is negative, and so forth for the work done. So here we have something called mechanical work. So you apply some force, you make some change to happen. So here it's like there is a gas cylinder with a piston attached, and this gas cylinder contains some gas, and when you apply some force, then due to this force, this piston moves by an amount like this from a position x0 to position x. So during this change, you changed its volume by an amount dV. So how much is the work done? The work done is F into dx, and then if you take the integration from x0 to x, how much you changed the position of this piston, and then you can get the full complete work done in this process. So that work done is W is equal to F dx integration, and then because you can convert every force into pressure into A, where A is the area of this piston, and inside this there is a pressure P. Then this P works opposite to the applied force, so that's why you have this negative sign here. And when you replace this F is equal to P into A, then you get A into this x minus x0. So this is this volume change, that is dV. So you get work done is equal to minus P dV, right? So this much, if you change, applying some force, if you change the position of this piston, then that's a mechanical work that you did, and that mechanical work is nothing but minus P dV, right? So here this minus sign is due to this opposite nature of this force and the pressure inside. Then with this you can now look at the first law of thermodynamics. So first law of thermodynamics doesn't have much. It was introduced by Gibbs in 1973. You see the development of, up to the development of this first law of thermodynamics, it's nearly like 75 years or so have taken when first people understood that work and heat energy are related. To put that in a formal, mathematical form, it took 75 years of development. So here the first law of thermodynamics says that, again, basically it's a conservation of energy. So it said if you do some work or if you add some heat, either of them, then it will change either work done or the heat, and also it will change some heat energy, or internal energy. So let's say I have given some heat energy to a system, then the system will do some work, and also due to that heat energy, its internal energy will change. And if I do some work within the system on the system, then its heat, there will be some heat change in its heat content will involve, and also its internal energy will change, right? So then you just change, as we have done here, the work, if it's a mechanical work, then you can write the first law of thermodynamics like this: du is equal to dq minus p dv, right? So with this, we end this session of thermodynamics. Thank you.